Yes. So I'm Pekka. I'm from Metosin, and I've been working here for the last couple of years now, I think. So.
We were told you're the only one at the office.
Yes, sometimes. Most times, yes. Yes. It's very almost like having a private office. Yes. So I'm gonna give a quick overview of data analysis in using this tool called Clojure. I suppose that's how you're supposed to pronounce it, I hope. And particularly, I'm not a real data scientist. I'm giving it more from a programmer's and an ex-physicist point of view. I used to study physics and write like particle physics Monte Carlo simulations some 15 years ago. So I actually revisited some of my own simulation codes and ran some of that stuff for the demo plots. So needed to generate some data. So, but yeah. So basically, when I first encountered Clojure around 2009, 2010 timeframe and looked at the REPL and the editor integration, it felt like this is a pretty comprehensive and awesome data analysis and like a workbench already in itself. So I'll just do some of my visualizations and analysis using this one and what could possibly go wrong. Now, of course, I discovered that a lot of the tooling wasn't there and it was pretty difficult, and I had to write quite a bit of custom code to make my things work. But things worked out pretty nicely back then. Back then there was a tool called Encounter that used the Java JFree chart library for visualizations, and it was pretty nice for the time. And but let's see what these newfangled new tools can do. So basically, I think Clojure has a lot of the basics right. It has like the interactive environment for playing with data and a lot of interop opportunities, especially with the JVM, but also with Python and some other things familiar or like famous in the data science scene. So it seems rather promising and pretty awesome story at least. And let's see how it works. So basically, I haven't shown this picture or this slide in something I showed like 16 years ago in a conference. Like this is basically what I was working on at the time. We had like a Monte Carlo simulation of what happens in the nucleus when you shoot like particles such as protons, neutrons, or light ions into a target of, say, lead or iron or whatever. And basically, we were simulating like binary collisions between particles in the nucleus and like tracked all those particles as they collided. Certain things could happen. They could elastically scatter from each other. They could like form these kinds of something we called delta resonances that could then decay further to pions, another type of particle, basically, for our purposes here. But basically. And then, of course, some particles, as they arrive at the boundary of the nucleus, they could either be reflected back in or be kicked out of the nucleus. And basically, this was like the first part of the simulation. Like, if my pointer is visible, it was this first part. And after this, we have like nucleus that has like some excitation energy. The particles are still going around with some excess energy. And what can happen next is we have a separate simulation code that deals with the de-excitation. The nucleus can fission into two nuclei, or it can like evaporate low energy, slower neutrons and protons and all kinds of things. So that's basically what the simulation itself does. The simulation code I wrote was in C++, and unfortunately not in Clojure and not in Haskell. But it was a step up from the previous version because a significant part of my job was to migrate an old Fortran 77 based simulation to this C++ code. So it was an improvement. And actually the C++ part was pretty convenient because we integrated this model then to a larger simulation framework that required C++. So that was basically the motivation for it. And here's an example of the kind of result that was something we commonly showed. And here we have, for example, carbon on carbon target at 135 megaelectron volts per nucleon collision. And then we're basically comparing the energy spectra of neutrons that come out of this simulation in specific angles and compare it with another model. This red one was our model, and then blue one was a competing model, and the dots are the data points from a specific experiment referenced somewhere here.
Question. If the red's your model, did you use your Monte Carlo simulation to train it?
We didn't actually train anything. There are different types of models. There are more data-driven models that were, well, not really, we didn't speak of training. It was more like fitting to data. But our model was like more theoretical, like let's say, kind of theoretical, but still an approximation. We, for example, treated particles as like point-like things that collide, have like binary collisions inside the nucleus. We weren't modeling the particles as any kind of like wave functions or some quantum mechanics stuff. So it was, but it was more theory-driven model. And actually, one of the things that was like one of the important points of the model was that it could, because it was more driven by theory, it could give, it had predictive power. It could give like results with good accuracy for things we didn't have data for. So it's a little bit different from like the usual data-driven data science type of stuff. But anyhow, so basically I ran this kind of simulation again, and okay, I got some data out of it. I had to actually do some data conversion to split up the data into separate files. It was a bit more convenient when using these more like CSV-oriented or table-oriented format. Like here, I wrote a separate little function to basically read the simulation output file and then parse it, and used actually Metosin's Malli library to coerce the data into suitable types of number things and that sort of stuff. So there was a little bit of data preparation, but then, okay, we can start inspecting this. This notebook is written using Clay. It is the notebook of choice in the Norge framework, and it's a pretty nice thing for from a programmer's point of view because I can just write all this stuff in my editor. You can use your editor of choice, and then the HTML page is generated. And that's I at least found that a bit nicer than these purely web-based notebook things that are often used. So we can print some stuff out of the data frames, and it's pretty easy to just print, for example, the first 10 entries in a file, and it just produces mostly readable output of the file contents, or the data frame contents. So it's pretty nice for inspecting what your numbers actually seem to be. And here I have, for example, in this events data frame, we have some general information about the event, for example, there is a calculation of, I think, energy balance. We did some calculation. One event is basically one projectile shot on a target and what comes out of that. So we were calculating, for example, the energy balance, how well energy is conserved. Energy should be conserved, but it's when you're dealing with Monte Carlo and floating point numbers and all that, you get interesting things. And sometimes probably there might be a large energy imbalance might indicate, for example, problem with the physics of the model, for example. And then, some of these remnant nuclei that are then given as input for the de-excitation model, and then the particles themselves that we are going to then look at. So we have basically, unfortunately, I forgot to sort these out in some sensible order. So these are in a little bit random order, but it doesn't matter. So we have, basically the main things that we need are the A and the Z, the mass number and the charge number of the thing. So if we have, for example, charge number 1 and mass number 1, that's a proton, and charge number 0, mass number 1 is a neutron, and that's a pretty conventional way of encoding these particle types in that field. So what we can do is, of course, we can write a little function that matches the A and Z to the particle row, and we can get the values from the corresponding columns and check that are they both matching to the A and Z we want. So, for example, if we want to match to a proton, we could write this kind of little helper function. And then if we take a quick look at what these would actually look like. So here we take the particle data set and filter all the protons. So we have now we're now looking at only the protons. And then we draw a histogram of the kinetic energies of these selected protons, and we get this kind of distribution. So in these particle physics circles, histogram is basically your number one tool a lot of the times. So those histograms and logarithmic scales really, which is unfortunate because a lot of tools don't deal well with histograms that have zeros in them, and then you put logarithmic scale, the visualization doesn't look so good. But for example, fortunately, the Plotly library used here in these examples worked out pretty nicely. There was another library called Hanami that didn't work so well, and unfortunately. And We can do the same, of course, with neutrons. And here we are matching to mass number 1, charge number 0. And again, we can do basically the same kind of plot. And we get a little bit different distribution here. So these are, for example, we can see that in protons there is a small peak just before like very low energies, and then it goes down here when we approach the energy 0, and with neutrons we don't have such a thing. It behaves very differently. So yes. Then as we have two models, we can of course do further filtering of the data. I could have, of course, chosen the neutron energy spectra and stored them in a separate data frame, and then I wouldn't have to filter again, but I decided to keep these extra steps for clarity. And we can have origin -1 in our simulation was the cascade, the first part, and then the origin 0 was the excitation, the latter, the second part of the simulation. Then if we plot here, we can take, yes, here are the cascade neutrons. We can see that, for example, we can also zoom these plots, so that's pretty nice. So we can see here that we don't have really so many low energy neutrons in this part. And then the energy spectra are going to a pretty high value, so we have pretty fast higher energy neutrons here. The spikiness of the histogram is basically caused by the fact that I didn't bother to run a large enough simulation. I could have made it smoother by running 10 or 100 times larger thing. But I was lazy and saved the computer's time. So we can of course do the same for the other part of the simulation, which is the origin 0, the de-excitation. It had a lovely name called ABLA V3P. I'm not sure where that came from, but anyhow, that was it. And then we can plot the energy spectrum of that. So we don't get very high energy particles from that at all, as would be expected. So we have pretty low energy neutrons coming from that. And of course, now that we have these things, we can combine them in the combined plot. So here we can see that we have the blue one is the total, and then the orange one is the cascade, and the green one is the excitation. So we can see, or we can put multiple things in the same plot and compare and see how they what they are made of. And we can, for example, we could probably calculate the sum of these, this histogram, summed content, like histogram bin by histogram bin, should result in this blue one. But I didn't check it, but I just trusted it. Now, at this point, yeah, I was pretty happy when I got that. I had to do a little bit of a helper function to combine the plots, because maybe this was my unfamiliarity with the tool, but I didn't find a better way to combine these histograms together in the same plot. So, but it was actually pretty nice that the plot contents are basically described as data, so you can pick it apart and combine it in new ways. So that was pretty nice. So of course now we are approaching the point where we have something similar, or are trying to do something similar as I had in my earlier slide about the results. But this is of course a different simulation with different inputs. This was actually a proton on lead target. The conference results were carbon on carbon. For our purposes, it doesn't really matter. So. But anyhow, we can write again a little helper function where we choose particles going in a specific angle, and we can define some acceptance window, because to select the particles, like if you want like particles going in the angle of 75 degrees, you choose like 75. Your acceptance is like 75 degrees plus minus 2 degrees or something like that. So to get enough like things in your histogram, and it will look better that way, and can be taken care of later in the calculation. I haven't done those calculations in this presentation, but anyhow. So this first plot was basically like we're using again the filtering like by angle in angle 10 degrees with plus minus 3.0 degrees, and we can get a histogram. Again, one that has a lot of spikes, so there aren't that many like particles that match this criteria, but there are some. Again, this would benefit from running a bit larger simulation, but oh well. And then we can do the same for particles in a little bit different angle. Now we can see that there are a bit more things in this direction of 90 degrees. And of course we can look at something else than neutrons. We can plot, for example, the energy spectra of helium-3 ions, and we get some. They are pretty large, so they have fairly small kinetic energy when they come out of the system. So that would be about what I'd expect to see. And here we have another one, like with the mass numbers, the combined number of protons and neutrons in a nucleus. And we can plot like, we can see that there are a lot of like protons, neutrons, light ions. Then there are like heavier like remnants that are, or heavier products, atoms that are produced, or nuclei that are produced from the evaporation. And then this little bump here, this is the fission products, the nuclei that come out of the fission. This is again, used to be one of our standard plots, and looks about like what I'd expect to see. Now then, after some time, I decided to then do a little bit of more data manipulation. So I added a new column. Actually, here is the neutron count, the mass number minus the charge number, the number of neutrons in the nucleus. So we can actually do a pretty nice little expression to add a new column to our data frame. And then we can use that for visualizations. And if we look at it, what it looks like, we have pretty much the stuff we had before, except that we have the neutron count here added at the end. And this one should be always this one minus this one. And then we can, of course, try to plot them. So what I tried to do next was I tried to draw a 2D visualization out of that, a 2D histogram, and then plot that as a kind of heat map. So we could see something like the proton numbers and the neutron numbers in a nice graph. And this one was a little bit surprising. I'm not sure if I was using it correctly or if there is actually a bug in the function. So I basically I wanted to basically see something like this. Well, part of it up to here maybe. So basically this is like the usual distribution of like stable nuclei and things around them that may decay radioactively. But this was really puzzling because I wouldn't expect the proton number to be so high. So I basically wrote my own version of I copied the existing implementation of this compute histogram and modified it a little bit. And then it produced something quite a bit more like what I wanted to see. So I decided it was more correct.
Yes, science.
Yes, yes, that's why that's how it works.
The usual approach in CERN when the data doesn't fit.
Yes, yes. Just yeah.
The information must not leave this room.
Yeah. Yes, yes. Need to destroy all recordings, or. But yeah. So I decided this one looked a little bit better and more like what I wanted to actually show. This picture is a bit larger than what I was showing, but anyhow, it worked out pretty nicely in the end, if we believe that I did my modifications correctly. And yeah. We can basically then, okay, I have some, looks like I have some old plot here. Yeah, this one wasn't supposed to be there. Nobody ever saw it. Yes, so we can also draw some pretty interesting like distributions from like two-dimensional data. I'm again using my own improved histogram function. And basically I'm plotting here like the components of the momentum vectors of the particles coming out of the simulation. And as the projectile particles are going in the direction of the z-axis in the x and y plane, it's kind of symmetric, which is what I would expect. So Again, we accept it, and then in the direction of like x and z plane, here the axis labels are wrong, but this is the z direction, so we have much more like a scattering in that direction. Again, in these plots that I was preparing, I used this histogram because I tried to do a scatter plot, but there were way too many points for the Plotly library to handle. So that was a little bit or slightly disappointing, I'm afraid. But yeah, histograms to the rescue again, I guess.
So Plotly could not handle that. Do you have any other like Clojure libraries that you would depend on in this case?
I'm not sure. I might go with something like the old JFree chart based, like basically something non-web based, maybe.
Also, what do you mean by couldn't handle?
There were so many points that it seemed to become really slow.
So the
So the rendering of the points was basically
Yep.
like super slow. So, but I was probably giving it way too much data. And so that's basically what I did with Clojure. Now let's take a brief look at the main competitor, or maybe I'm not sure, mainstream tool in this domain. It's something called Root. It's the CERN C++-based data analysis framework. A very unorthodox piece of C++ software.
In which way?
It's basically built around an introspection system that offers the basis for its REPL-like environment, and also uses that to make it able to store basically any C++ object graph or large collections of these object graphs, which is how in the large particle physics experiments the collision events are represented. So it's pretty impressive piece of tooling, and here I actually, and it's possible to add your own classes with some additional macros, and there is a C++ interpreter involved and all that kind of stuff. So you can integrate new things with it. But so just for fun, I visualized basically in a 3D scatter plot of these momentum components. Okay, in this case for neutrons. Each one of these small points is one little point. I didn't unfortunately calculate the count of the points, but it's quite a lot. And this tool, of course, is built around local native graphics, so it can handle a lot. So just a simple example of how I might use it. So I can call the tool and give it a data file as argument. And then I can, for example, define a histogram with specific kind of binning. And then I can just I have a data, let's call it a data frame. They call them trees but whatever. So I can use this ET is a tree that has just been defined in the file, and by my simulation code. And then I can just plot the kinetic energy of all protons and direct it into this H1 histogram. And just like that, a plot appears. Now, this, of course, is one other unorthodox thing that they do. They have basically these domain-specific language like string arguments that they use for like making the selection of data. This thing here would be like the equivalent of the filter thing I was using in my Clojure code.
It looks like C++.
Yeah, it looks like C++. Yeah. Or it looks like particle physics C++, which is different. This tool is somewhat unorthodox and has been criticized, especially by more software engineering-minded people. For example, for the use of elaborate string arguments that are like mini languages in themselves, and lots of global variables, and also like data things like histogram classes that inherit a whole bunch of visualization and graphics things, which is probably backwards as far as mainstream software engineering is concerned, or that's at least some of the main criticisms. But yeah.
Did you try the 3D plotting in Plotly? Because I used Clay and some plotting library, maybe Plotly, to draw some nice 3D line graphs. in a previous project. And it was pretty good actually. You could spin the cube around and zoom in and everything.
Yeah, I did experiment with that one. I forgot to add one of those. That would have been pretty good demo.
I was surprised because those were maybe the best interactive 3D plots I've seen, because previously I had done 3D plots in something like GNU plot and it's just horrible. Actually interact with it, I mean.
Yeah, it's. I did look at some of the examples and it was pretty good for that. And I should have probably added one of those. But one thing. But again, for example, in this case, I would have probably had way too many points to.
Would have needed to sample it or somehow.
Yeah, that's like what I used histograms for in this 2D examples stuff. Yeah, but it was overall a pretty nice experiment and experience. I was pretty satisfied with the tool as such. But in this particular domain, I encountered some issues also, like the sensitivity between the log scales and the zeros. It was a little bit too picky sometimes with those. Plotly worked better, but And then, as I was a little bit unfamiliar with this tool, one of the issues was that I used it wrong a lot of times, and then it just resulted in an empty plot. So maybe it would have been nice if there had been some error messages, but
probably will just give empty.
Yeah. Also, Clojure and error messages. It's an interesting history. So I guess, it's a perfect storm of error messages, but yeah. Then another thing is that these, unlike these data science default or usual data science tools that Notch is maybe modeled after, the official CERN tools basically have the default mentality that you never want to load all the data into memory. So they are pretty good at processing data, large amounts of data with small memory. You don't have to load all of it into RAM to process it. So something like that would be nice, but also quite involved to develop with, especially if you want this kind of fairly nice pipeline-like workflow. So, yeah, but maybe it would be an interesting problem to work on free time or something. But yeah, and of course the things I really enjoyed was the Clojure dynamic environment. You can basically take hold of any data and open it up and see what it's made of, and that's basically how I developed my custom histogram function, by looking at things like just what the stuff was made of, how does this pipeline work, what do these functions expect and return, and so on.
Until finally the result was what you wanted.
Yes, exactly. That's the thing. And a lot of for example, in the I'm not sure if I can call this tool mainstream, but for particle physics it's mainstream. These cuts or data selectors that I use, and also here I could have used some fancy formulas to, for example, normalize the results to some specific unit system or whatever. It's these little mini languages in the strings are actually quite nicely replaced by some basic functional programming things like, for example, map filter functions as first-class citizens and that sort of thing. And also this these macros for composition and function composition. These are pretty nice things to do when you're playing it with data, and it's something that many of the mainstream tools, at least in the C++ world, don't really easily support. But yeah, I suppose that's it. Any questions, or are we heading straight for the drinks?
Why not both?
Well, yeah, that's the best way.
Can we plot the amount of people who went for drinks and who went for more questions?
I think we don't have the necessary tracking system in place. We could make a simulation of it, yeah.
Yeah, maybe I have a question around. Oh, sorry. Is there another question? Go for it. Yeah. Is there more about like a rough idea of like performance? Like how long did it take to like, let's say you would rerun that book, you have all the formulas and everything. Is it like a few minutes, or is that like hours of crunching, or?
This one is actually not even minutes, so it was pretty quick. So I was rather happy with that.
Does it support incremental changes? So if you make changes in only one place, that it doesn't re-render the whole HTML?
I think it re-renders the things, yes, because at least in my workflow, I had the notebook open in Emacs, and basically I was connected to the Clojure REPL, and then I ran one Emacs function that runs the Clay updating logic. So I think it doesn't really support incremental changes, but at least it didn't in my workflow. But yes.
It's just HTML. You're not kind of limited to this feature because you could just generate few HTML codes, not snippets but blocks basically, and then you just concatenate them into a single book. So it's
right.
also possible.
Yeah. Yeah, that's something. Yes.
For your simulation, so for this representation, you rerun the simulation back in C++. It's not being run in Clojure.
Yes, I ran the existing C++ simulation. I didn't rewrite I don't remember how many thousand lines.
Is you written the entire simulation by hand, or did you use a library like Stan or something like that?
We wrote it by hand. It's like custom, fully custom simulation. So old-fashioned style.
Yeah. So, but then you did convert it from Fortran, so.
Yeah. It was we basically redesigned the simulation code, and it was part of the basically the main part of the project to rewrite in C++. So for better maintainability and other things. So yes.
Sampling was mentioned earlier, and since we are doing data science here, I would be interested in hearing how the sampling would work, since there were no examples of doing random sampling there in the Clay itself.
That's a good question.
I mean, it might also make some of your graphs render better.
Yeah. That could work. Yeah. This was pretty basic. I haven't looked into this custom sampling. Basically, you can write as there are in these pipelines. There are I can call basically my custom functions here. So I could basically write any kind of thing I want for the data processing pipeline at least. And basically this is just, all of it is just basically normal Clojure code, at least on my side. So basically it would be possible to do whatever one wants but I'm not entirely sure what are all the facilities offered by this framework to do these kinds of things, like automatically.
I would assume the framework would offer the random sampling. It's a pretty basic thing.
Yeah.
to
Yeah,
do.
yeah. Yeah, there probably are some like
Maybe
tools.
there should be, because most data science workflows have some function allows you to just sample directly rows. You don't even have to specify
right.
what you're sampling for. You can just basically it samples from the index of the data structure itself directly.
Yeah, there probably is some. I just didn't end up using any or familiarizing with myself with those yet.
Well, if you want to iterate on this, you could do that for a 3D plot to happen.
Yeah, probably. Yeah, that would be a good exercise.
For the next meetup.
Maybe.
Do we want to go over the data science with Clojure in 2 meetups in a row? Would then be the question.
Yeah, probably not.
On the Haskell side, I know that there are some, like this is sort of timely because I know there's a few people who are trying to improve the data frame workflow stuff. I'm not too familiar with it. I've just seen them talking about it in the Haskell discourse forum.
Yeah, there was already this Data Haskell project from 2016 or 17 or something, but then I think it ran out of steam a bit, and now there's a new enthusiastic maintainer. Yeah, yeah, it's very interesting to see where that is going, and yeah.
Yeah, I think that's good.
Yes.
Release the tension.
Yes. Thank you.